Energy is the ability to do work. The average American has available the energy equivalent of about 150 slaves working 24 hours a day. Materials that store this energy for work are called fuels. Some fuels contain more energy than others. This is called energy density. Of these fuels, oil is the most critical. The world consumes 30 billion barrels a year, equal to 1 cubic mile of oil, which contains as much energy as would be generated from 52 nuclear power plants working for the next 50 years. Although oil only generates 1.6% of US electricity, it powers 96% of all transportation. In 2008, 2/3 of America's oil was imported. Most was from Canada, Mexico, Saudi Arabia, Venezuela, Nigeria, Iraq, and Angola. Several factors make oil unique. It is energy dense. 1 barrel contains the energy equivalent of almost 3 years of human labor. It is liquid at room temperature, easy to transport, and usable in small engines. To acquire energy, you have to use energy. The trick is to use smaller amounts to find and extract larger amounts. This is called EROEI, energy return on energy invested. Conventional oil is a good example. The easy to extract, high quality crude was pumped first. Oilmen spent the energy equivalent of 1 barrel of oil to find and extract 100. The EROEI of oil was 100. As the easy-to-find oil was pumped first, exploration moved into deep waters, or distant countries, using increasing amounts of energy to do so. Often, the oil found now is heavy or sour crude and is expensive to refine. The EROEI for oil today is as low as 10. If you use more energy to get the fuel than is contained in the fuel, it's not worth the effort to get it. It is possible to convert one fuel source into another. Every time you do so, some of the energy contained in the original fuel is lost. For instance, there is unconventional oil, tar sands and shale. Tar sands are found mainly in Canada. 2/3 of the world's shale is in the US. Both of these fuels can be converted to synthetic crude oil. However, this requires large amounts of heat and fresh water, reducing their EROEI, which varies from 5 to as low as 1.5. Shale is an exceptionally poor fuel, pound for pound containing about 1/3 the energy of a box of breakfast cereal. Coal exists in vast quantities and generates almost half of the planet's electricity. The world uses almost 2 cubic miles of coal a year. However, global coal production may peak before 2040. The claim that America has centuries' worth of coal is deceptive, as it fails to account for growing demand and decreasing quality. Much of the high-quality anthracite coal is gone, leaving lower-quality coal that is less energy dense. Production issues arise as surface coal is depleted and miners have to dig deeper and in less accessible areas. Many use destructive mountaintop removal to reach coal deposits, causing environmental mayhem. Natural gas is often found alongside oil and coal. North American discovery of conventional gas peaked in the 1950s and production peaked in the early 70s. If the discovery graph is moved forward by 23 years, the possible future of North American conventional natural gas production is revealed. Recent breakthroughs have allowed the extraction of unconventional natural gas, such as shale gas, which might help offset decline in the years ahead. Unconventional natural gas is controversial, as it needs high energy prices to be profitable. Even with unconventional gas, there may be a peak in global natural gas production around 2030. Large uranium reserves for nuclear fission still exist. To replace the 10 terawatts the world currently generates from fossil fuels would require 10,000 nuclear plants. At that rate, the known reserves of uranium would last for only 10 to 20 years. Experiments with plutonium-based fast breeder reactors in France and Japan have been expensive failures. Nuclear fusion faces massive technical obstacles. Then there are the renewables. Wind power has a high EROEI, but is intermittent. Hydropower is reliable, but most rivers in the developed world are already dammed. Conventional geothermal power plants use existing hotspots near the Earth's surface. They are limited to those areas. In the experimental EGS system, 2 shafts would be drilled 6 miles deep. Water is pumped down one shaft to be heated in fissures, then rise up the other, generating power. According to a recent MIT report, this technology might supply 10% of US electricity by 2050. Wave power is restricted to coastal areas. The energy density of waves varies from region to region. Transporting wave-generated electricity inland would be challenging. Also, the salty ocean environment is corrosive to turbines. Biofuels are fuels that are grown. Wood has a low energy density and grows slowly. The world uses 3.7 cubic miles of wood a year. Biodiesel and ethanol are made from crops grown by petroleum-powered agriculture. The energy profit from these fuels is very low. Some politicians want to turn corn into ethanol. Using ethanol to supply 1/10 of projected US oil use in 2020 would require 3% of America's land. To supply 1/3 would require 3 times the area now used to grow food. To supply all US petroleum consumption in 2020 would take twice as much land as is used to grow food. Hydrogen has to be extracted from natural gas, coal or water, which uses more energy than is generated from the hydrogen. This makes a hydrogen economy unlikely. All the world's photovoltaic solar panels generate as much electricity as 2 coal power plants. The equivalent of between 1 and 4 tons of coal are used in the manufacture of a single solar panel. We'd have to cover as many as 140,000 square miles with panels to meet current world demand. As of 2007, there were only about 4 square miles. Concentrated solar power, or solar thermal, has great potential, though at the moment there are only a small number of plants operating. They are also limited to sunny climates, requiring large amounts of electricity to be transmitted over long distances. All of the alternatives to oil depend on oil-powered machinery, or require materials such as plastics that are produced from oil. When considering future claims of amazing new fuels or inventions, ask, does the advocate have a working commercial model of the invention? What is its energy density? Can it be stored or easily distributed? Is it reliable or intermittent? Can it be scaled to a national level? Are there hidden engineering challenges? What is the EROEI? What are the environmental impacts? Remember that large numbers can be deceptive. For example, 1 billion barrels of oil will satisfy global demand for only 12 days. A transition from fossil fuels would be a monumental challenge. As of 2007, coal generates 48.5% of US electricity. 21.6% is from natural gas. 1.6% is from petroleum. 19.4% is from nuclear. 5.8% is from hydro. Other renewables only generate 2.5%. Is it possible to replace a system based on fossil fuels with a patchwork of alternatives? Major technological advances are needed, as well as political will and cooperation, massive investment, international consensus, the retrofitting of the $45 trillion global economy, including transportation, manufacturing industries and agricultural systems, as well as officials competent to manage the transition. If all these are achieved, could the current way of life continue?